Hello my YouTube friends, today we're going to look at application of Laplace transforms in electrical circuits, and this is a very interesting subject and topic that enables students to simplify the solutions. Instead of using differential equations, you simply use algebraic equations according to the Laplace transforms. So let's dig in and see what we get. So from here, we first of all have to understand that Laplace transform was pioneered or was used or was formed by Pierre-Simon Laplace, and it was named after him. And it's a powerful tool that is very useful in electrical engineering. It was actually made very popular in electrical engineering by Oliver Hillside, who made this very popular. So what this does is it allows you to convert the time domain calculations into what we call the S domain or the frequency domain. And the frequency domain is basically algebraic equations. And so after we do the frequency domain, we solve the solutions in frequency domain, we have to convert them back into the time domain and we get our solution. Now, as I mentioned, you might see that the Laplace domain or the S domain is a complex domain, which forms the S in this case is sorry for that. The S in this case here is a complex domain which composes of the real or the transient part plus the imaginary part, which is the yod omega as the steady state, and here is the transient part. So then this is what happens. Now when we come to look at the transform itself, what is the Laplace transform equation? So what you see here is the Laplace transform. So we're transforming the function from the time domain into the function of the Laplace, which is the S or the frequency domain, and this is how we obtain our equation. Now S has dimensions of frequency, which is in hertz, or it can be put as inverse seconds, which is what we have here, and the lower limit here implies the time just before time is equal to 0, that is the t 0 minus. And when the Laplace is applied, like I mentioned, you are going to have differential equations that are in the function, the time function or the time domain function are replaced by algebraic equations, which makes it easier for you to solve and come up with the solution in algebraic format, and then you change that now back into the time format and you get your solution, and that is how we go. So after you get your solution, you have to inverse the Laplace transform. This is our inverse Laplace transform. So we inverse the Laplace, which is the algebraic equation, back into the time domain, and we use this equation to do that. But in most cases, you realize that the tables, the lookup tables or the Laplace transform pairs are enough for you to get the solutions that you are required to get when you're done doing the Laplace equation. And that's what we are going to stick to. So we're going to stick to you using the tables, and we're going to have enough solutions provided by the tables. I don't think we'll need to come to use this equation. So therefore, this is the procedure, and you realize that the equation that we looked at, the Laplace transform equation, in there the function of time is ignored for time is less than 0. This ensures that the function is multiplied by a step unit, a u at t, which is simply 1 over s, and that's what we are doing. Now Let's look at the procedure of getting the Laplace solution. So what you do, the transformation process, is that you've got a time domain. So you've got a circuit in a time domain described by a differential equation. You transform that circuit to a Laplace circuit, or an S domain, or its frequency domain, into a circuit in S domain. So you've got a circuit in time domain, you have to transform it into an S domain circuit, which is described by algebraic equations. Then you solve. So after you solve, you get your solution, and then after you find your solution, which is expressed in frequency domain, you convert or transform that back into the time domain, and you obtain your final solution. So previously, when we looked at second and first order circuits, we focused on just the time domain, and we looked at this time domain. We're using differential equations to directly get our solution in the time domain. But in this case, we take this route where we first convert into the frequency domain, find the solution in the frequency domain, and then convert back into the time domain. And this is, in most cases, I would consider this procedure an easy route, and this is slightly difficult for some of our students. So that's the procedure. And now let's look at elements. So when we come to the resistor, is time and frequency invariant. That implies that the resistor is not changing with the time, between the time domain and the frequency domain. So if we look at this circuit, you have the resistor here in the time domain, you have the potential difference here between the resistor, which is VRT, and then the potential difference here is Vs and the resistor. So when we take look at Ohm's law, our voltage source, or our voltage value, the voltage across the resistor, which is Vs, here is equal to Is multiplied by the value of the resistance. And if we take the ratio Vs divided by Is, we simply get resistance, which is R. So there's no change in terms of the value of resistance, or in terms of the resistance, even when you do the Laplace of that value of resistance. So the resistance stays the same. However, when we look at the other two elements, the inductor and the capacitor, we experience something a little bit different. What we see here is the time and complex frequency domains change, and therefore for a purely inductive circuit, you see that we have a difference in terms of the value or how we calculate the inductance in the time domain and the inductance in the frequency domain. So in this case, when we take the time domain, our voltage across the inductor VRT is simply going to be the inductor value, L dit over dt, and the voltage across that inductor is going to be SLI at S in the Laplace domain. And when we compare the ratio to solve, so we're using the voltage divided by the current, and this gives us SL. So you get the IS cancelling out, and you remain with simply SL, which is what we have obtained here. So in this case, the Laplace of the inductor will be equal to SL, and that's what we get when we get the Laplace of the inductor. And this leads us now to looking at this inductor circuit. So in the time domain, what we have, we simply have an inductor. There's a voltage across that inductor, which is V at T, and then we have a current going through that inductor. Now what happens is that when we're converting from the time domain to the frequency domain, we can have two options depending on the circuit and depending on how you want to solve your solution. In certain cases, it will be easier if you choose the inductor in series with the voltage source, because you simply use certain methods. Let's say if you're using mesh current method or nodal analysis, this might be easier. If you're using another method, even the mesh, same nodal, may be easier for one of you to follow, and you can adopt this pattern. So what happens is you've got two options, which is B and C. You can convert to either an inductor in series with a voltage source, or you can convert to an inductor in parallel to a current source. The direction of the current source is going to be in the same direction as the IS, or by convention coming out of the positive terminal, and in this way it's in that direction. And these are the two options that you have. So you notice that the voltage source value is calculated from Li at 0, which is the initial condition, and then similarly here the current value is calculated from the initial conditions, which is I at 0 over S. And that is how we solve these. We utilize these two choices. And so a comparison of the calculations then follows that if we look at the time domain, we've got the voltage source value shown in this way, and we can get the current value IL at t to be solved from 1 over L by the integral VL dt. Whereas if we come to the S domain, and if we consider the first solution that we picked, which is the inductor in series with the voltage source, what we get here is that we've got the potential VLS, or the voltage across these two terminals, being equal to the potential at the inductor subtracting out the source voltage value from here. So you've got SL multiplied by the current, which is the potential across the inductor, minus LIL 0 minus, which is before time t is equal to 0. And equally, you could get the current value obtained like so. And then we can also look at further. The next element is the capacitor. So similarly to an inductor, you find that in the time domain, it differs from what we get in the frequency domain. So in the time domain, we've got I at t equal to C dVt over dt. This is in the time domain, and we get the voltage in the time domain still as Vt equal to 1 over C from t0 to infinity it dt as the voltage value. But when it comes to the S domain, when we transform to the S domain, we have our Vs equal to 1 over C, 1 over S, I, S when transformed. Sorry for that. And therefore, when we get to solving or comparing the ratio, what we get now is when we compare V over Vs over Is, which is equal to 1 over Sc, and therefore the Laplace conversion of the capacitor is equal to 1 over Sc, and that is what we adopt. Similarly, when we come to comparing the inductor and the capacitor, you find that when we're converting the time domain to the frequency domain, we have the same choices as we had with the inductor. So we're going to have two options that you can pick from. Now you must notice the differences in polarities between the inductor and the capacitor, and that should be hide the notes and you pay attention to that. So what we get in the time domain, we can convert to either capacitor in series with the voltage source, or we can have a capacitor parallel with a current source, and we can use that now to determine and find the solutions. And so if you look at the comparison between the domains in terms of how we get the values, we find that in the S domain, ICS is equal to SV VC, which is this value across this whole portion, and this subtracts the voltage across that voltage source together with the capacitor value, which in this case is the C. And from there, we are able to determine the VC as S to be equal to 1 over C, S over SC plus VC 0 minus over S. And that's how we get to define our solutions. And then to solve now, first you have to understand that we identify with these two, which is the SL and the 1 over SC, as the complex inductive impedance and complex capacitive impedance. So this is the inductive impedance, and this is the complex capacitive impedance. And SC and 1 over SL are also called complex capacitive admittance and complex inductive admittance, respectively. Now, to analyze a circuit, like I mentioned, there are 3 stages that you have to follow, 3 steps. First, you transform the circuit from a time domain circuit to a frequency domain circuit. And secondly, you solve the circuit using any preferred method. You can have node analysis, mesh analysis, source transformation, superposition, and etc. And then lastly, you can take the inverse transform of a solution using tables and obtain the solution in the time domain. And that is how it is done. And so I'll show you examples later on. Thank you for watching. Subscribe to my channel. I hope you enjoyed the lesson. Good day.